In this video, we're going to talk about the derivatives of some of the transcendental functions. So first off, let's start talking about the exponential functions. An exponential function is just a function of the form f of x equals some number a to the x power. Okay, so for instance, 2 to the x. One thing is you can't confuse this with the power functions. These are sort of the opposite of power functions in some sense, right? Power functions were x to some number power. Here the x is up in the exponent part and the base would be a number. So if you have an exponential function, the derivative of it, the derivative of a to the x power would be a to the x times the natural log of a. Again, we're not going to go through the proofs of any of these facts. We're just going to kind of, at this point, accept them as facts and then start taking the derivatives of these functions. Okay, so here's an example of an exponential function. The function is f of x equals 2 to the x power. Okay, so again, a lot of people, when they're first learning about these, they try to use the power rule, right, on exponential functions to take their derivative. You just can't do that because these things are not power functions. You have to use the fact that we talked about up here. So if you have a exponential function 2 to the x power, then the derivative is 2 to the x times the natural log of the base, in this case 2. Okay, so that's how that works. In calculus, we really like the natural exponential function, and that is f of x equals e to the x, right? Remember, e is an irrational number, right? 2.71828. So in between 2 and 3, a little bit closer to 3, right, than it is to 2. And if you use that number, e, as your base, then what you'll wind up with in this formula is the natural log of e, and the natural log of e is equal to 1, right? And so the derivative of e to the x is just itself. It's its own derivative. So for calculus, this is the best base, right, that you can use because it just has a simple format to it. So for calculus, this base here is just one of the best ones to use. Okay. You can't really talk about the exponential functions without talking about their inverses, right, which are the logarithmic functions, right? Remember, a logarithmic function is a function of the form log base a of x. If you have a logarithmic function, then its derivative is going to be 1 over x times the natural log of the base. So for instance here, if I have f of x equals log base 2 of x, then the derivative of that would be 1 over x times the natural log of 2. All right, and just like with the natural log, with the natural exponential function, we have the natural logarithmic function, right? That's usually denoted as ln, right? But it's equal to log base e, right? Is what it is. And so when you take the derivative of that one, you get 1 over x, and then the natural log of e is equal to 1. So you just wind up with 1 over x. So again, for calculus, this is the best logarithmic function because it has a simple derivative here. Okay. So if you've ever wondered, back when you took algebra or pre-calculus, why you bother talking about the number e as the base to an exponential function or the natural logarithmic function, right? Here is where you really start to see the advantage or how nice these functions are. When we're talking about calculus, they have simple derivatives. E to the x and the natural log function, right, both have the simplest derivatives of any exponential or logarithmic function. Next up, we have the trigonometric functions. And again, these facts assume that you are measuring the angle in radians, so we will always assume that in this class unless a problem specifies otherwise. So you should always assume that these are in radians. And again, that's a nice reason for measuring angles in radians, is because it makes these derivative facts work out pretty nicely. So the derivative of cosine is going to be the negative of sine of x, or negative 1 times sine x. The derivative of sine is just cosine. All right, for the other functions that are slightly more complicated, the derivative of tangent is secant squared of x. The derivative of secant of x is secant x tangent x. And the derivative of cosecant is minus cosecant cotangent. The derivative of cotangent is minus cosecant squared. So you can see with the tangents and secants, there's a little symmetry going on here. The tangents, the derivative of tangent is secant squared. The derivative of cotangent is minus cosecant squared, right? The derivative of secant is secant tangent. The derivative of cosecant is minus cosecant cotangent. So they sort of follow the same pattern. Also, you can see that the derivative of any of the co-functions, right? Cosine, cosecant, and cotangent, they all have the minus sign attached to them there. Okay? So those are the derivatives of the trigonometric functions. And the last group of transcendental functions that we'll talk about are the inverse trigonometric functions. Here we have all 6 right here. And you can see there's a lot of patterns to this also. The derivative of inverse cosine is minus 1 over square root of 1 minus x squared. The derivative of inverse sine, right, is almost exactly the same but without the minus sign in front of it. The derivative of inverse tangent is 1 over 1 plus x squared, so it has a really nice derivative. Kind of not what you would expect, right, at first glance. And if you look at cotan inverse here, it's the same as the derivative of tan inverse with the minus sign in front. Secant inverse has a fairly complicated derivative, 1 over the absolute value of x times the square root of x squared minus 1. And you can see that the derivative of cosecant inverse, right, it's almost exactly the same as the derivative of secant inverse. It just has the minus sign out in front there again. So again, we're not going to go over how all this works just yet. We're just going to take these facts for right now and then start taking derivatives. So let's take a look at an example here. And basically, this is just practice at dealing with the derivatives of these transcendental functions. So here I have a pretty complicated function, right? It's 7x to the 5th plus 7 to the x power minus 6 inverse cosecant of x plus 4 times the natural log of x minus 8 times the cotangent of x. So there's a lot of pieces involved in here, but it's actually not too bad because all of the pieces are either being added together or subtracted together. So I can use the sum rule and the difference rule, and all I would need to do is to take the derivative of each piece and then add or subtract. All right, so there's the original function, and now we're going to go through and take the derivative. So right here I have the derivative of 7x to the 5th, right? So that's the constant multiple rule. I would just rewrite the constant 7, right? And multiply by the derivative of x to the 5th, which is 5x to the 4th power. Okay. Then I would add, now take the derivative of 7 to the x power. Well, that's an exponential function, right? And so the derivative of that would be 7 to the x power times the natural log of 7. Okay. Then I would subtract off the derivative of this piece right here. This piece is a constant, right? 6, right? So I just rewrite the 6 using the constant multiple rule, and then I multiply by the derivative of inverse cosecant, right? Which is minus 1 over absolute value of x times square root x squared minus 1. Then I would add the derivative of 4 ln x, again using the constant multiple rule, right? That would be 4 times the derivative of ln x, right, is just 1 over x. Then I would subtract the derivative of 8 cotangent x, right? Again, using the constant multiple rule here, we'll just have minus 8. And then the derivative of cotangent is minus cosecant squared x. Okay. And here there's just some minor simplifications that you should do. go ahead and multiply out that 7 times 5 and get 35. Here I could I have a negative and a negative, and I could go ahead and multiply this 6 up top here. So just doing those minor simplifications here, I would get here 35x to the fourth plus 7 to the x times natural log of 7. Really nothing to do there. Here negative 6 times that negative will give me a positive 6, and then times 1 will give me a positive 6 up here. Here I could multiply that 4 times 1 over x, right? So 4 times 1 over x. And again here I have a negative times another negative. That would give me a positive 8 cosecant squared x. Okay, and so that's it. So just some minor simplifications there by multiplying, and that's the derivative of the original function.